All right, we're going to switch over now to our two invited speakers, or invited talk sessions. So first up, we have Amanda Glazer, assistant professor in the Department of Statistics Data Sciences at the University of Texas, Austin, earned a PhD in statistics from UC Berkeley, and previously also worked for 4 years as a baseball operations analyst for the San Francisco Giants. At UT, she teaches an undergraduate sports analytics course and conducts various research in sports analytics with a focus on injury risk and performance evaluation. Let's give a warm welcome then to Amanda.
All right, thank you. Can you all hear me okay? All good? Okay, great. So thanks, Ron, for the introduction. So today I'm going to be talking about some recent work in Changepoint detection. So I'll be talking primarily in the baseball context. So I'll start by talking a little bit about how performance is looked at in baseball. We're going to zoom in on a few specific metrics. So on the batter side, we're going to talk about plate discipline. On the pitcher side, we're going to talk about fastball velocity. And then I'll talk about what change point detection is from a statistics perspective and how we can apply it to the sports context. And there's a lot of kind of interesting challenges that come up when we try to apply it to sports data. And we'll talk about those and kind of how you address that. So in baseball, there's a ton of different metrics we could look at here. So as I'm sure most of you know, there's pretty detailed data recorded on every pitch, swing, play recorded in baseball. So traditional metrics, I've got a little picture of a box score here. So the box score in baseball, this was from the late 1800s. It's kind of interesting. It was a modified cricket box score. So that's where it came from. And the goal was just to show what happened. So to use data to illustrate what happened in the game using statistics. And so kind of these early metrics, we have what happened. So kind of the outcome of a particular at-bat or plate appearance. So if you hit a single, a double, a home run, what happened? And so we've got metrics like batting average, earned run average, which are telling us about what happened, what was the outcome of that particular plate appearance or that particular inning. Then we've got more advanced metrics. So there's tons we could look at in baseball. So there's some that are going to look at what should have happened. So these are the expected stats we see across sports that are trying to average out for things like, you know, a fielder made an amazing catch that maybe they would only make 10% of the time. And so we want to still give credit to the batter for that. So kind of averaging some of that noise out, capturing what should have happened. We've got metrics like WAR that are trying to change the currency of what we're looking at. So look at things in terms of wins or runs, things that we actually care about because it's related to the team winning. So kind of weighting our outcomes by that. And then we've got metrics that are going to capture a player's process. So today we'll talk about plate discipline. So looking at what they're doing at the plate, the outcome of particular swings. So it's kind of an outcome in a way, but a little bit removed from exactly what happens in the plate appearance. So the key thing with these metrics is they summarize a player's ability over some period of time. So a lot of times you see things at the game level, at the season level, but a player's ability can change. And so a lot of times we'll make kind of simplifying assumptions around that. Maybe that player ability changes season to season. You know, we look at aging curves for different ages of a player. But in reality, the player's ability can change at any time. And we'll talk about reasons for that. So we want ways to detect those shifts in player performance at any time within a season. So I'll talk about just the metrics we'll look at with this today that I'll give some examples on. So plate discipline is basically a player's ability to be selective with their swings. So you want batters swinging at pitches that they know they can hit well and not swinging at pitches that they can't hit well. And so that's a measure of that process. How good are they at identifying a pitch that they might be able to hit well? So there's two metrics we'll look at. There's a bunch of plate discipline metrics we could look at, but I'm just zoning in on two for the sake of this example. So chase rate, so that's looking at whether the batter swings at a pitch located outside of the strike zone. So we've got a strike zone here. So a pitch that would be a ball outside of the strike zone, if they swing at it or not. So you want a lower chase rate so that they're not swinging at pitches outside of the strike zone as much. And then whiff rate, so looking at every pitch that they swing at and then whether or not they fail to make contact with it. So again, you want a low whiff rate. You want generally players to be making contact with pitches that they swing at. So those are two metrics we'll look at today. And then the other thing we'll look at is fastball velocity for pitchers on the pitcher side. So four-seam fastball is generally the fastest, straightest, most frequent pitch that a pitcher throws. Why this is generally of interest, a couple reasons. So higher speeds tend to be correlated with better pitcher outcomes. Year to year, we've been seeing a rise in fastball velocity and just pitch velocity across pitches in general. I pulled this figure just from an ESPN article that's focused on pitcher injuries, but it's talking about just the rise in the average pitch velocity across pitch types. And so another kind of interesting tie-in with this is that there's also this hypothesis that increased pitch velocity is related to pitcher injuries as well. So there's some idea that by tracking these changes, we might also gather information about whether a pitcher is at risk of being injured. It can also be helpful to look at in terms of recovery from injury and stuff like that. Okay, so those are the metrics we'll look at. So now we'll talk a little bit about change point detection. First, more generally, how you apply it, and then the challenges in applying it in a sports context. So why do we want to look at this? So like I mentioned, a player's performance is not fixed. It changes over time, and it can change for a lot of different reasons. So as they get older, it can get better. Usually we see it gets better to a point in baseball, usually till the late 20s or so, and then it tends to decline. That'll vary across metrics. It could drop after an injury. Certain performance attributes might get better or worse before an injury, so it can be helpful for kind of injury detection potentially. It could improve after a mechanical adjustment, so they make some change to the way they approach their swing or the way they pitch, and then their performance improves. So that's another reason it can change. So detecting these changes across different metrics can be really useful for a lot of different reasons. So a big one is player evaluation and development. So with your own players, knowing, they make a particular mechanical adjustment, we want to see, did this translate into outcomes? Are they actually performing better after having made this change? And so being able to track that for your own players is really useful. And then if you're on a team, and then if you're looking at other players, so maybe you're trying to think about players to acquire, being able to track when they've changed is really useful. And in baseball, we've got a lot of players across the minor leagues, majors, some of them we might be more focused on and see those changes, but you've got a lot of minor league players too, and you're probably not looking at all of them across all of those metrics on that level of detail. So ideally, we'd like an automated way to go through and flag those changes for players we might want to keep an eye on. So that's a big reason it's useful. Like I mentioned with injuries, so there's a lot of potential there to track changes that could tell you a player's at risk of being injured. So looking at when they shift out of kind of what their baseline was, if we know certain kind of, an increase in velocity or something like that could lead to more likely a UCL tear, we could monitor for that. And then just, thinking about within your own team roster decision-making, when players have gotten better or worse, having a handle on that. So the goal is to detect when those changes occur, separating the genuine shifts in performance from random noise, because there's going to be a lot of noise here for a lot of different reasons that we'll get into, but we want to find when those shifts are most likely to occur and not just flag everything because the data is noisy. So how do we do that? So we can use change point detection methods, and there's a lot of literature about this in statistics, but the gist of it is, for a player, we have a time-ordered sequence. So this could be maybe their fastball velocity by pitch. We order it by time, and we want to identify a point, if it exists, so a point in time where we think before that time, the data comes from a particular probability distribution, and after that, the distribution shifts. So in this case, I'm primarily concerned with shifts in the mean. So I think before a time point, the player's true fastball velocity on average is different than after that time point. So I'm trying to find shifts in true underlying ability. So the examples we talked about, looking for shifts in fastball velocity, looking for shifts in chase rate, whiff rate, we want to find when that true underlying parameter changes, if it did change. So we're searching for that time point. So there's several different ways you could do this. So one way you can do it is by looking at likelihood ratios. If you don't know what that is, don't worry. I'll kind of give it in a more general sense. But basically, there's two hypotheses here when we look at a particular player's data. We could think that all of them come from one model. We've got one true underlying average here. There is no change. That player ability is constant over this time period. Or the alternative is that there is a time point where that player's true underlying ability shifts, where it gets better or worse. The average goes up or down. And so we can use something called a likelihood ratio, which is basically assessing which model makes the most sense. So, how likely is it that actually we do have a split at a particular time point, that the data comes from two different distributions versus no split, there's no change, it comes from one distribution. And so intuitively, larger values are going to mean that it's more likely that there was a change. Smaller values are going to be say that it's more likely that there was no change. And so we're looking for larger values of this test statistic, and we're searching for that player for that time point that's going to maximize that. So I'll show you a really simple example of this. So here, this is just made up data. I'll show you some real data in a little bit, but we could assume this is fastball velocity here. We have it by pitch. We see that, it's got some variance. It's not a constant velocity across pitches, but we could search along here, look after every time point and figure out at what split of this data is it most likely that we see that true average shifting. So here, there's a pretty nice separation. So by eye, we can kind of see this pretty well that at this time point 50, we think there has been a shift in the average. And so before we saw an average of about 93, and then it goes up to 95. So we're just looking across all those time points and figuring out when is it most likely that we're coming from two distributions instead of just one. Great. So what is the problem with this when we apply it to sports data? So in practice, the challenge here is that we can find the most likely time point for a split. Then what do? How do you determine if that's truly a change point? So typically, what people will do is they'll apply some sort of criteria. So whether that's a threshold or a hypothesis test, so maybe you apply like a t-test to before and after that change point to see if the means are significantly different, to say if this is a statistically significant change point. Do we think this is a true change point or just, kind of the best fit we could get for the data? So in practice, when we do this, the issue is we tend to really overflag change points, and I'll show you examples where we flag basically every pitcher. So you do this even if you apply, a hypothesis test, different penalties to the change point detection, you tend to way overflag the number of change points, and so suddenly we've gone from something that's pretty cool to something that's just not usable at all. When you give someone thousands of players that you flag every day on different metrics, what are they going to do with that? So, maybe we're okay with a little bit of overflagging because probably at some point someone's going to go through and review those changes, look into those particular players, but we don't want it to be that we're flagging hundreds of players and no one can parse through that. And that's what happens in practice when you apply these models. So we need some way to cut that down, kind of knobs to twist where we can lower the type 1 error rate, so lower our false positive rate, and also ideally some way to kind of threshold the changes we look for. Maybe we don't care about an increase, even if it's legitimate, of 0.1 miles per hour in fastball velocity. We really just want to look at changes greater than 1 or greater than 2 miles per hour. So kind of giving us more control over what we're flagging and feeling a little bit better that what we're flagging is legitimate. So a kind of side issue too, so a lot of implementations of change point detection algorithms in R and Python, they make a lot of assumptions. So a lot of them assume a normal distribution. They don't work super well with binary data. It's a pretty easy fix. You just kind of have to change out the distribution you're assuming. Binary data is great because it draws from a Bernoulli distribution, but a lot of the existing packages don't work super well with that. So we want something that's computationally tractable, not going to overflag players. It's going to run quickly, it's going to work with binary and continuous data, and it's going to let us adjust that sensitivity to change points. So it's a pretty relatively simple fix we can do that really is going to cut down our change points. And it's something called split sample inference. So it's really related, if you've done a prediction problem before and you've had a training and a test set, the reason you split that is you don't want to use the same data you train a model on to test it. tend to overfit, inflate your type 1 error rate, et cetera. So we're going to do the same thing here. It's just a little bit different. So we're going to divide things into even and odd indices. So we're going to go through using our likelihood ratio, detect the change points using our odd indices. So if this is 6 pitches here, for example, we're going to use pitches 1, 3, and 5 to find the change point. And then let's say we find it after pitch 3. This is kind of an unrealistically small example, but you could imagine having hundreds of pitches, finding it after a certain pitch number. And then we go to the even indices, look at that same time point and test it. So we test for that difference in means there. So now we're splitting out the data, so we're not using the same data to find the change point as we are to test for its significance. And another benefit too, when we do this, we can look at not just whether the average changes, we could also look at a particular threshold. So see, does the average after the change point increase by a certain amount or decrease by a certain amount? So that gives us a little bit more control over the magnitude of changes that we're looking for. One quick note too, so I'm mainly talking about this in terms of one change point. You can pretty easily extend this to multiple change points. So the thing you do here, it's called binary segmentation. So basically you go along, you look for the first change point. So in this case, we find it right here. We split it, and then we're gonna go into each side of the change point, look for a change point again, and keep doing that process until we no longer find change points. So after this step, we look here for a change point. We don't find one, so we stop on that side of the data. We look for a change point here. We do find one, so then we would look in this segment and this segment for a change point, and then keep going until we no longer find change points. So in practice, you might not even need to do that if you're just looking along for a change point. You find one for a player and then you keep looking, but especially if you're looking back over historical data, you might want to do that. Okay, so now I'll show you some results on this. So for the plate discipline metrics, I looked across all MLB batters in the 2023 and 2024 seasons. I looked at their chase rate and their whiff rate. And I looked at it both with and without sample splitting. And so if we don't do the sample splitting, we still have a significance test there, but we're not separating out that train and test data. We're flagging a lot of batters. So over 70% of them, that's reduced by about 88% if we implement that sample splitting. So this is cutting down the change points by quite a bit. So we're filtering out a lot of those false positives, which is great. So it makes a huge difference, especially in this case. And I'll give you an example. So this isn't quite what's going in to the algorithm because it's going to be those zeros and ones, but if I plotted that, it would look kind of crazy, just this up and down. So I just did a rolling kind of average of the last 50 swings, so it was a little bit easier to visualize. But here's one example of Bryce Strings whiff rate. So this is across the 2023 season, and we can see the algorithm flags a change point in July where his whiff rate goes down. And so it's able to take that binary data, find that change point. It's significant even once we do the sample splitting there. And if you look at his year-to-year data, you'll see kind of that change from 2023 to 2024, but we're able to flag it kind of mid-2023 with this. And kind of interestingly from this too is we can see how frequently changes occur in the middle of the season versus at the beginning or the end of the season. And what we found is that actually a lot of them occur in the middle of the season. So over 60% of them are occurring in May through August. And so this really makes you think about some of the assumptions we make about changes happening year to year, or maybe more likely to occur in the off season. There's a lot of changes that we're finding, in the middle of the season. So in terms of thinking about player evaluation, something to keep in mind there. So for fastball velocity, so like I mentioned, we can look at not just whether the averages are different before and after the change point, we could also look at some thresholds. So to see if it's changed by more than a mile per hour, or half a mile per hour. And this is really helpful, especially here, because you'll see when we look at this, that the sample splitting doesn't help as much in this case. I think because there's a little bit less variance in some of those rate statistics, but thresholding, it helps a lot. So 2024 MLB season, I just looked at starters, and First, just looking at kind of the same thing we did with the plate discipline, with and without sample splitting, we still flag a lot of pitchers, so it doesn't decrease by as much as we saw with whiff and chase rate. But what we do see is when we start to look for particular changes above a mile per hour, we cut down the number of change points by quite a bit. So now we've got this way to really threshold how sensitive we want to be to changes, especially in metrics where we think there might be legitimate changes more frequently. So really helpful there to kind of control the number of change points we're finding. Okay. Oh, and here too, 57% of the changes are occurring in May through August. So kind of the same type of thing where we've got a lot of these changes in fastball velocity. This is specifically four-seam fastballs that are occurring in season, in the middle of the season. So how do we validate this? So I'm telling you this and you might be wondering, okay, well, you know, she could still be flagging incorrect change points. We could be missing change points. How can we validate this? This is really difficult because you need some sort of ground truth data. You know, I could simulate data for you and show you that it works. A lot of times that's kind of contrived because I can make examples a certain way. But some sort of ground truth data would be nice. That is tough because changes can occur for a lot of different reasons. So for a pitcher, let's think about their fastball velocity. It could increase as he builds strength, increase or decrease due to a biomechanical change to his approach, decrease as he ages, decrease due to an injury. It could also increase or decrease due to a change in role because we've got starters and relievers. And this is really helpful because we know when that change in role happens, and so we can use that as ground truth here. So we've got relief pitchers that pitch much, much fewer innings than starters. So relief pitchers typically pitch like an inning. Starters will pitch, you know, about 5 or so. And pitchers will transition sometimes from a relief to a starting role. And so what happens when they do that is their pitch volume goes way up, and because they're throwing much more pitches, they tend to do that with much less intensity. So their velocity is going to go down. And so this is a change that it's not guaranteed that their velocity will go down, but we have a little bit more confidence that that probably is going to happen, and it's pretty well documented that that tends to happen. And so this is something we could look at to see these role changes with pitchers, if we're able to flag them, what threshold we're able to flag them at. So I constructed a list of 11 pitchers where there was a pretty clear role change sometime in 2023 or 2024. And I went through and saw for their primary fastball if we were able to flag their change point. And for all of them, except for Soriano, which I'll show you and talk about why, we were able to flag that change. For most of them at pretty high thresholds. So there were 2 pitchers that it flagged at that 0.5 mile per hour, but most of them we were able to flag with at least a 1 mile per hour decrease. So that's at least some validation that what we're doing is working, that we haven't totally cut out legitimate changes where we know there should be a decrease in velocity. And so I'll show you these examples. So the biggest change was with Jordan Hicks. He had a pretty massive decrease in his sinker velocity of just like about 5 miles per hour, I believe, 5.5 miles per hour. So there's a huge difference there. When he became a starter, that was a really easy one to flag. There's gaps here just because of time, but in practice, the data you give it would not have that gap in there. And then Soriano, we don't flag. There's a very small difference there. There was also some changes in his pitch usage. So he started relying on his sinker slightly less. So that could be part of what was going on there. It's like a little bit confounded, but this isn't a place where we would think we would find a change visually. It doesn't look like there's much going on, so maybe we feel a little bit better about not flagging that. So hopefully I've convinced you that change point detection is feasible in this setting. It's really difficult just because sports data is really noisy. We tend to really over flag things, but there are ways to kind of constrain this, reduce the false positive rate. So we saw it for a couple metrics, plate discipline metrics, fastball velocities. We saw that a lot of these changes occur in season, which have a lot of implications for player evaluation. And we use this ground truth data set of those reliever to starter transitions to validate it. But there's a lot of future work here. So there's not a ton of work in this space. There's a lot of opportunity. So instead of those likelihood ratios, we could consider other test statistics, other ways to detect those change points. that rely on less assumptions. There are some alternatives to sample splitting. Some of them are a little bit computationally intensive, but there are other things we could do there to, kind of compare the power and the false positive rate. And then one big thing, so the metrics I chose here are less likely to be influenced by other factors. They will be a little bit, but like fastball velocity shouldn't be influenced too much by your opponent in ballpark. There are a lot of metrics that will be, so being able to incorporate that into the change point detection algorithm is an important next step as well. So you're not just flagging changes in those conditions. And then something I'm currently working on is combining this with causal inference methods to look at the impact of velocity increases on pitcher injury risk. So a lot of exciting work. Hope this was interesting to you all, and happy to take any questions.
All right, let's thank Amanda. We got time for some questions. Oh, this should be a good one.
Thanks, Amanda. That was really cool. I guess when you're talking about the sample splitting,
yes.
you described this kind of even-odd index pair.
Yes.
And I'm just curious, how sensitive are these algorithms? Are you, in practice, averaging over multiple random splits, or are you really just fixing even-odd each time?
Yeah, so all the results I showed, it was doing it once, so just one even odd split. That's an interesting idea. You could try to do it over a bunch of different splits and kind of see how that changes things, but for this, it was just looking at that one split.
All right.
Hi, thank you. I know you said that it can be computationally heavy. What are you guys using using Python, R? Are you doing it by hand to find these computations? And then kind of my little backup to that is, what distributions are you finding most in your data? Are you finding normal, or are you finding other kind of distributions in your data?
Yeah, good question. So I implemented all of this in R. I have done Python versions of it as well. So you would want to implement it in one of those, just so you don't want to be doing any of this manually. So either R or Python would work for this. So for the distribution, so for the rate statistics, so anytime we're looking at kind of a proportion, a rate of something, you would assume that every swing or pitch, whatever kind of the denominator is a Bernoulli distribution. So that kind of like coin flipping distribution where there's some probability of success. And that fits really well for that, because that's exactly what's happening. There's some true underlying probability of an event happening. For fastball velocity, I assumed a normal distribution, which fits it decently, but I think there are a lot of interesting kind of non-parametric alternatives in Changepoint where you don't actually have to assume any sort of distribution when you're flagging the change point. So that's kind of a next step, is to get away from even those distributional assumptions, because there are going to be metrics where it doesn't fit in well with a normal distribution and it's not a Bernoulli distribution. You would need something else.
Hey, thank you. Have you observed a correlation between your change points and, say, like post-injury or post-trade to another team, or between off seasons? Because I could imagine it might be the case that after an injury, or if you're traded to another team, you might have a jump in your performance in some way.
Yeah. So I've definitely noticed it and looked into it really explicitly with injuries, because that's a big interest area for me. So that's definitely something that I've observed, where you see, especially too before the injury, a lot of times you can see a change in some performance metric before the injury occurs. And so that's a lot of work that I'm doing now, is to figure out what are ways we can detect that and hopefully prevent injuries before they happen by flagging when certain metrics decline. But just, going through the data and seeing what it flags, I have seen that, just, looking through it, that there has been a relationship there for sure.
Thank you so much for joining us today. I was really curious how you found that Jordan Hicks, I believe, has very minimal amount of change points. Are you finding that really successful players have very minimal change points? They're very consistent in their practice. They're not going through as many mechanical changes. Or are you finding that there's a certain average of change points that you can tend to expect from really successful players?
Yeah, so I haven't calculated the numbers on how many change points we're seeing for particular players. It's an interesting question, but I would say change points can happen for different reasons. So even a very successful player, you're going to see a lot of changes because they're going to be getting better. They're going to be making changes that are going to improve their performance. And with any player, good or bad, you're going to see changes as they age. And those can occur kind of at different times, not necessarily at the season end or beginning. So I think regardless of good or bad, you're going to see changes due to aging, due to improvement, due to decline. So there's kind of a number of different factors. But it's an interesting question. I haven't looked into exactly, what types of players you flag the most change points in, but I like that question.
One more question from Steinberg. Sam?
Okay, go ahead. You can use the ceiling mic. Just speak loud.
I would say how
Little loud.
how much does weather affect like the actual pitcher at a certain ballpark?
Well, I missed that.
The question, Sam, can you just repeat it?
Yep. The question was about the specific ballparks and the effect of weather potentially playing a role in the observed metrics and that therefore influencing
Yeah,
change point detection.
Yeah, it's a good question. So it definitely could, and that's an area for future work is to incorporate that, especially with metrics that you think are going to be more influenced to that. So as soon as we start looking at anything related to the outcome of a plate appearance, there's definitely going to be ballpark effects there. So I pretty intentionally chose metrics that I thought would be less influenced by that. So fastball velocity shouldn't be as influenced by that, I would think, and same with plate discipline metrics. So that was an intentional choice. There are ways to incorporate those other factors. So, your particular opponent, the ballpark effects, but you would have to include that in that change point detection algorithm itself. But that's kind of a next step.
All right, let's thank Amanda for a fantastic talk.